Okay, so thank you very much for giving me the opportunity to speak. So I want to talk about joint work with Carolina Araujo, Ana Maria Castravet, Ivan Cheltsov, Kento Fujita, Jesus Martinez-Garcia, Kostya Shramov, Hendrik Süss, and Nivedita Viswanathan. This has appeared as a preprint on the Max Planck server with the number that's written here. So I want to talk about K-stability, which is a notion that was introduced to characterize the existence of Kähler-Einstein metrics on Fano manifolds. So I won't give too many definitions, but please feel free to interrupt if needed. I'd like to get to the algebraic bit. So the theorem that was proved a few years ago by Chen, Donaldson, Sun, and independently by Tian, which was known as the Yao-Tian-Donaldson conjecture, is that if X is a Fano manifold, then X admits a Kähler-Einstein metric, and if and only if X is K polystable. Now, this is an equivalence of really deep properties in algebraic and differential geometry, which are little understood on both sides. So the question we started thinking about was which Fano manifolds are K polystable. So in dimension 2, we know that there are 10 deformation families of smooth del Pezzo surfaces. In dimension 3, there are 105 deformation families of smooth Fano threefolds, with a description that is, in a sense, birational due to Iskovskikh, Mori and Mukai. So this provides a fantastic testing ground and a fantastic experimentation ground to understand better this notion. So the questions we looked at were the following. So considering a deformation family of Fano threefolds, is the general member of F K polystable? A refined version of this question is which members of F are K polystable? And then the kind of longer term question is there a moduli space or a moduli stack representing the elements of F? So here's, in a sense, what's known. Here, we know the answer for all families. So this was known before our work in many cases, in about 50% of cases. Here, for the second question, the refined question, we have a complete picture so I'm talking about dimension 3 here. We have a complete picture for 71 out of the 105 families, and I'll come back to that. And for the third question, a kind of construction of compact moduli, there are very few cases known, so this is mostly open. I'll discuss one case on which there was some progress recently. So let me go back to what we proved in that preprint and perhaps to the refined answer, or to the answer to question 2. So what do we expect to happen in the cases that we don't know, which is what I'd like to focus on today? We expect that for 27 out of the 34 families for which the Calabi problem is not entirely solved, for 27, all smooth members are K-stable. So here, in a sense, our expectation is built upon the fact that we cannot make examples of non-K polystable Fanos in these families. Now, for the remaining 7 families, so these are families 110, 220, 221, 222, 35, 38, and 312, then we know that these families have K polystable general member, but they also have some non-K polystable members. And I'll talk a little bit about some of these families. So maybe just let me flag here that this is the family of prime Fano threefolds of genus 12. So the famous V22 that are the subject of Donaldson's conjecture. So I'll come back to that later in the talk.
Can I quickly ask a question? So if you're right, they have K polystable members. Does that mean that the above, they have all, like every member is K polystable?
So we expect that all smooth members. So then there's a separate question, which is when you build a compact moduli space, you might include some non-smooth members as K semistable degenerations, and those might be K semistable, but here in all the other 27 families, we expect that all smooth members are K stable.
Thank you.
Okay, so let me talk about known obstructions, or like the classical theory. So let's go back to dimension 2. So smooth del Pezzo surfaces, we have a very good description of these. So the smooth del Pezzo surfaces of degree D have the following form. So P2 blow-ups of P2 in a bunch of points, or P1 cross P1. And we have an explicit description in many cases. Now, one of the first obstructions that was known to the existence of Kähler-Einstein metrics, which is where this whole subject started, was that if you had a Kähler-Einstein manifold, then the automorphism group was reductive. This was extended by Alper-Bloom, Halpern-Leisner, and Schuh, who proved that when X is a K polystable Fano variety, actually, then the automorphism group of X is reductive. So going back to the cases of del Pezzo surfaces, there are exactly two of these which have non-reductive automorphism groups. So because of the very explicit description, the automorphism group is in many cases fairly is easy to get explicitly. So here we have an automorphism group which is non-reductive with semi-direct product of GA square by PGL2. Whereas here we have an automorphism group which is isomorphic to the product of two Borel subgroup semi-direct mu2. So these are the two cases where the automorphism group is non-reductive. And the result due to Tian is that all smooth del Pezzo surfaces with reductive automorphism group are K polystable. So all smooth del Pezzo surfaces, apart from this blow-up of P2 in a point or blow-up of P2 in 2 points, are known to be K polystable. So this is, of course, so there are quite a few, or there are some Fano threefolds with non-reductive automorphism groups, and this is already a first result that they are not K polystable. But so I've given you an obstruction to K stability, K polystability, but I haven't yet told you what this is. So let me go back to the first definitions of K stability in terms of degenerations. So a test configuration of X minus RKX, where R is an integer, is an abstract one parameter subgroup flat degeneration. So this is a pair, curly X, curly L over A1, where X is a family over A1. So X has a flat proper GM equivariant morphism to A1, pi. L over X is a GM equivariant pi-ample line bundle. And when we take out the central fiber, we have essentially a product. So X minus X0, the pair X minus X0 and the restriction of L to X minus X0 is isomorphic to X minus RKX multiplied to the product with A1 minus 0. So this is a picture of a test configuration. And so there's somehow an easy example of, so of course you have the trivial test configuration, which is just the product of x minus rkx with the affine line A1. But an interesting case of test configuration when you do not have, which is non-trivial, is the following, that of product test configurations. So if you imagine that you have a Fano threefold or a Fano variety more generally, which has an effective GM action, then taking any integral co-weight of this GM action, of this GM, will give you a test configuration where you take the product of X with A1, the line bundle minus the anti-canonical line bundle of the product, and the GM action being given by T acting on the pair XA by TX, T times A. So this is a product test configuration. So let me go to the definition of K-stability now. So to any test configuration, you can associate an invariant, which is called the Donaldson-Futaki invariant. So there are a few definitions of this invariant, but I won't go into it. So we say that X is K-semistable if this Donaldson-Futaki invariant is greater or equal to 0 for any non-trivial test configuration. It's K-stable when it's strictly positive for any non-trivial test configuration, and it's K-polystable if it is K-semistable and the Donaldson-Futaki invariant being 0 forces XL to be a product test configuration. So what I should... So going back to my product test configuration, it's actually not very hard to show that the Donaldson-Futaki invariant of XL is 0 in this case. So the easy first consequences of these definitions is that you see that as soon as you have a product test configuration, your Fano cannot be K-stable. So as soon as you have an effective GM action, your Fano variety will not be K-stable, but it might be K-polystable. So if X is K-stable, the automorphism group of X can contain no subgroup isomorphic to GM. And if the automorphism group is finite, actually the two notions of K-stability and K-polystability end up being the same. Okay, so this was the first definition of K-stability, which was in terms of degeneration. And in a sense, what's very hard about this, this definition is that it's a definition in terms of all possible test configuration. The first result, I think, that appeared that kind of indicated that this notion had something to do with birational geometry or could speak to birational geometry was a theorem due to Odaka, who showed that, so you can, of course, define those notions of K stability, semi-stability, polystability for singular varieties. You're not limited to manifolds. And Odaka showed that a K semi-stable normal Q-Gorenstein Fano variety is always Q Fano. So it has Kawamata log terminal singularities, KLT singularities. So as I said, the difficulty in the definition of K stability is that you have to look at all degenerations, all test configurations. And if you've ever looked at degenerations of Fano threefolds, you know that in particular, one of the issues is that you can bubble up in the central fiber. So in particular, your central fiber has no reason to be irreducible. So this led to the introduction of the notion of special test configuration, which is a test configuration where the central fiber is Q Fano. In particular, it's irreducible and it has KLT singularity. So a special test configuration is a degeneration with a not too bad central fiber. so as examples, if I was to look at degenerations of smooth quadrics in P3, so here I've written two degenerations of smooth quadrics of a smooth quadric surface in P3. X squared plus y squared plus z squared plus t omega square is the special degeneration of the smooth quadric to the quadric cone, whereas the second test configuration is actually non-special because it ends up with two planes in the central fiber. Okay, so theorem due to Li and Xu is that if you have a test configuration of x minus RKX, which has negative or zero Donaldson-Conjecture invariant, then you can find a special test configuration with negative or zero Donaldson-Conjecture invariant. So if you are looking at questions on stability of Fano varieties, then you can limit yourself to special test configurations. So test configurations, degenerations with irreducible central fiber. Okay, so another important shift in the perspective on these notions on stability came with the work of Fujita and Li, and with essentially the shift from a definition of stability in terms of degeneration, so all degenerations of a Fano varieties, to a definition in terms of valuations of your Fano varieties. So let's look at this notion, which is the one that's in a sense easier to use for algebraic geometers. So taking a Q Fano variety, so X here is assumed to have KLT singularities, particularly its normal. A divisor E over X is a prime divisor on some proper normal model of X. So if you've been in birational geometry for a while, that's a B divisor on X. So to every divisor over X, so you can associate an invariant, which is called the Betaine variant, which is defined as A of E minus S of E, where A of E is the log discrepancy of your divisor. So E, the divisor, is an actual honest divisor on this model Y. We're taking A of E to be 1 plus the order along E of the relative canonical KY over X. And the second entity here, S of E, is actually the expected order of vanishing. So it's 1 over the volume of your Fano variety minus K to the N of the integral from 0 to infinity of the volume of f upper star of minus Kx minus TE dt. So this integral is actually an integral only while the volume of this makes sense. So in order for this volume to make sense, you want this to be pseudo-effective divisor. So this integral actually only goes to the pseudo-effective threshold of your divisor E, and this S of E is an expected vanishing order. Of the canonical along E, if you like. Okay, so the Betaine variant is then defined as the difference between this log discrepancy and this expected vanishing order along E. And the theorem due to Fujita and Li is that X is K-stable if and only if the Betaine variant is strictly positive for every divisor E over X, and it's K-semi-stable if and only if the Betaine variant is greater or equal to 0 for every E divisor over X. So now we've replaced our definition of K stability, which was in terms of all degenerations of a, or all test configuration of a Fano variety, by a definition in terms of all proper divisor, all divisors over a variety. So this is really a definition in terms of valuations of X. And I guess it doesn't come as a massive surprise that degenerations of X should be related to valuations of X. Okay, so the reason, one of the reasons why this recasting in terms of Betaine variant is very useful. So I should say as well that there are some other invariants that are related to valuations. I've chosen to just define the Betaine variant here, but there are some other invariants and some other criteria, such as the delta invariants, that are used in particular by Abanzwang and others. So here, but in general, the general way this is used for Fano threefolds is that this is particularly strong as a criterion when your Fano threefold or your Fano variety has symmetries. And this is due to, so a sample theorem in there is due to Data, Liu, Sekalehidi, Zhu, and Zhuang, and says that if you have reductive automorphism group, and if the beta invariant of every divisor over X, which is Otex invariant, is strictly positive, then X is K polystable. So if you want to check K polystability or prove that something is not K polystable, then you have to focus on those valuations or those divisors over X which are invariant under the automorphism group. So the larger the automorphism group, and some Fano threefolds have very large automorphism groups, the easier the question is to answer. Okay, so let me go to, you know, in terms of these Betaine variants. So here we've seen that the Betaine variant, so the Fujita-Lee criterion tells me that something is K-stable or K-semi-stable when the Betaine variant satisfies a certain inequality for every divisor over X. Now, let me consider then the first obstruction you can think of to K-stability. This is a notion which is due to Kento Fujita, which says that X is divisorially K unstable if you have a divisor on X, which has negative Betaine variant. So you don't need to go to models over X. The divisor actually lives on X. And Fujita examined all Fano threefolds and noticed that there are 26 deformation families of Fano threefolds with divisorially K unstable members. So the way he proved this is really interesting in that he just went and looked at the Mori and Mukai classification. There have been you know, it's possible from the Mori and Mukai classification to extract essentially the shape of all pseudo-effective cones of Fano threefolds. And he just went and looked at all possible divisors and their Betaine variant and found the deformation families of Fano threefolds which had divisorially unstable members. And in a sense, the absolutely surprising, I think, thing is that when X is a general member of a deformation family of Fano threefold, then either X is in a maverick family, you always have a maverick when you deal with Fano threefolds, or K polystability is actually equivalent to divisorial K semistability. and is equivalent to K semistability. So this easy obstruction, in a sense, this kind of which of those families are the ones that fail the Fujita-Lie criterion in the most obvious way, are basically those that fail the Fujita-Lie criterion, full stop. So I should say that, you know, so for Fano threefolds, basically this notion of divisorially unstable families basically catches all the deformation families except one that fail, that are non-K polystable, that have non-K polystable general member. For this is true, of course, for Del Pezzo surfaces as well. And here's an example of how one of these computations goes. So let me look at a divisorially unstable Del Pezzo surface. So I'm looking at the blow-up of P2 in 2 points, P and Q. I call the map to P2F. Then you have 3 - 1 curves on this surface. So the exceptional divisors over P and Q, and the proper transform of the line through P and Q. You can write that the anti-canonical divisor is linearly equivalent to 3L plus 2E1 plus 2E2, so that it's easy to see that the pseudo-effective threshold of L is 3. So this is the maximum T such that minus KS minus TL is still pseudo-effective. It's easy to see as well that for T between 0 and 1, minus KS minus TL is still NF, so that the volume of minus KS minus TL is just the top intersection product. Now, when T is greater than 1, between 1 and 3, minus KS minus TL is no longer NF, but it's not too hard to actually explicitly determine the Zariski decomposition of minus KS minus TL. And you find that the NF part is 3 minus T times L plus E1 plus E2, and the negative part is what's left over. So that the volume of minus KS minus TL is just the top intersection product of its NF part, is 3 minus T square. Now, if you compute the expected vanishing order, you find 25 over 21. Because L is a divisor on the variety itself, on the surface itself, its log discrepancy is just 1, so that here the Betaine variant is strictly negative. You would find an entirely similar picture if you were to just compute the Betaine variant of the -1 curve on the blow-up of P2 in 1 point. So in the paper on the Calabi problem, similar calculations are made for a large number of Fanos, and I guess this is also what's done by Fujita in his original paper. So let me discuss a little bit stability in families. So the key question here is, how does stability vary in families? So we've got, maybe before I move on to stability in families, are there any questions? So here I want to talk a little bit about how stability varies in families. And so there's quite a few results already about this. So a number of results that have appeared from, Xu and his collaborators, so Bloom, Liu, Xu, Zhuang, in various combinations, have proved that if you have a flat family of Q Fano varieties over Z, then the locus where the fibers are K-stable is Zariski open, the locus where the fibers are K semi-stable is also Zariski open, while the locus where the fibers are K polystable is constructible. Another important result is the uniqueness of K polystable degeneration. So if you have a Q Fano X, which is K polystable, this is equivalent to saying that X is K semi-stable, and that any degeneration with K polystable central fiber of X has actually central fiber isomorphic to the variety you started with. So the question we're interested in is, what does K polystability or K semistability mean geometrically? And the longer term goal is, can we understand moduli spaces and semistable degenerations of families with K polystable members? So let me go back to this, sorry for the seasickness. So in our main theorem, we had that either X was K polystable if and only if it was divisorially semi-stable, or X was belonged to family 226. So I'd like to discuss family 226 just for a second, because it has it illustrates a number of these ideas. So family 226 is obtained by blowing up a line on the Del Pezzo manifold V5. So the intersection of the Grassmannian 2,5. So Grassmannian 2,5 is Plucker embedded in P9. If you take a general intersection with a linear subspace of codimension 3, you have you obtain a threefold which lives in P6, and that's V5, the Fano manifold, the Del Pezzo manifold of degree 5. So V5 basically has no moduli. It doesn't move. And there's a fairly good description of it's a Grassmannian, so there's a fairly explicit description of lines connex on it. So you have lines of two types, and these lines have either a normal bundle of the form O plus O, so a balanced normal bundle, or they have a normal bundle of the form O minus 1 plus O1. So this gives you two different threefolds when you blow up this line, which are the two elements of family 226. So in the Mori Mukai description, the second side of so this is a Fano threefold of Picard rank 2, so it has two extremal contraction. The other extremal contraction is the blow up of a quadric in a twisted cubic lying on it. So it's a quadric living in P4. So one way to differentiate between those two lines is that essentially you always have, so this C3 is a twisted cubic on this side, and C3 lies on a unique hyperplane section of my quadric. So it lies on a unique quadric surface. And basically, if I have a line with balanced normal bundle, then my hyperplane section of this quadric on which C3 lies is smooth. It's not very hard to show that that C3 has an effective, that X1 has an effective GM action. And you can build a degeneration of X1 to some Q Fano variety X0, which has an effective GM square action. And so here, this is, you can show that X0 is a complexity 1 T variety, and so there's an arsenal of techniques to study the K stability of these, and so you get that X0 is K polystable. Now this X0 is actually singular, so it's not isomorphic to X1. So by openness of the locus where, so by openness of K semistability, you can conclude that X1 is K semistable, but it's not K polystable because it's not isomorphic to X0. So here X1 is strictly K semistable. I should say that this X0 is essentially obtained by degenerating the quadric surface on which C3 lies to a quadric cone, as in the special degeneration that I wrote earlier. So in the second case, when we have an unbalanced normal bundle, the quadric surface on which C3 lies is actually singular. It has a singular point that lies on C3. And the automorphism group of X2 is a semi-direct product of GM by GA, so it's non-reductive. So that X2 is not K polystable by Matsushima's obstruction theorem. But you could ask, is it K semistable? Well, it's actually not K semistable either. And this is obtained by, so it is divisorially K semistable. There's no divisor on X2 for which the Betaine variant is negative. But if you look at the pre-image of the singular point on the left-hand side here, so here you had a singular point P that lied on the twisted cubic. Take Z to be the pre-image of the singular point. And blow up Z, then you find that the divisor you obtain here is not K semistable. Has negative Betaine variant, so that X2 is not K semistable. Okay, so so in a second, I will talk about some of the families for which we know that there are both K polystable and non-K polystable members in the same family. So I wanted to discuss a recent example of a modular construction, which is due to Liu and Shu. So I think this appears in 2019. And they showed that essentially the K moduli of cubic threefolds coincides with the GIT moduli. So if I consider a cubic threefold, X3 and P4, then it's been known for a while, so it's an observation, I think, of Paul and Tian, that if X is smooth and K polystable, then X is GIT polystable. What Liu and Shu proved is that if you have a possibly singular cubic hypersurface, which is GIT polystable, then it is K polystable. And if it is GIT semistable, it is GIT semistable. Sorry. Then it is K semistable. So in particular, you obtain a description of, or you obtain a good quotient that parameterizes all K polystable threefolds that are smoothable to a cubic threefold. And you get an explicit description of singularities that can appear on K polystable degenerations of cubic threefolds. And the idea of the proof is to understand the singularities that can appear on degeneration. So you have a link between the global volume of a K semistable Fano variety and local volumes of singular points, which is a relation that was proved by Liu and which takes this form. And you can get an explicit bound for KLT non-smooth threefold singularity volume. So basically you go back to Miles Reed's description of threefold terminal singularities, for example, or of threefold KLT singularities, and you kind of go through case by case. So for example, you have an explicit bound for KLT non-smooth threefold singularities, which says that the local volume is bounded above by 16 with equality if and only if you have an A1 singularity. So then they use this to show that all degenerations, such degenerations can be embedded in a suitable explicit ambient space, and then you can use GIT and show that K polystability is actually the same as GIT polystability. Okay, so in a sense, this is an indication of what could work for a lot of hypersurfaces, in particular, where you have where you hope to be able to use similar ideas, where Paul and Tian's results will still hold and tell you that something which is K polystable is going to be GIT polystable, and where you hope to be able to go the other way, to go back the other way, by a careful study of local singularities. Okay, so let me talk about one such case where you have both K polystable and K semistable members and non-K polystable members. So this is family 224. So these are hypersurfaces of type 1, 2 in product of P2. So we have a complete description. So basically, if you look at this from the Mori and Mukai perspective, you have that these are Fano threefolds, which have two conic bundle structures. One of them is actually a P1 bundle structure. The other is a real conic bundle with a discriminant curve and so on. Studying forms for these discriminant curves lets you show that you can write down the smooth members in one of the following three forms. So either X belongs to a one-dimensional family, X mu, of this with equation of this form. So here mu is taken to be in C, mu cube is not equal to -1. So I should say that these requirements that mu is in C and mu cube is not equal to -1 is only have to do with X mu being smooth. So if you consider mu equals infinity or mu cube equals to -1, you still get KLT Fano varieties that are in these deformation families. And then you have two special cases, Y1 and Y2. And Y1 and Y2 both have special degenerations to the fiber over 0 of this family X mu, so to X0. So you can show that there's an effective GM square action on X mu when mu is 0, 2, or plus or minus 1, plus or minus square root of 3. You can show that you have an effective GM action on Y2 and finite automorphism group for everyone else. And what's known is that here X mu is K polystable for all mu, including the ones that correspond to singular values, so mu cube equals to -1 and at infinity. And Y1 and Y2, which have degenerations to X0, are therefore strictly K semistable. And of course, here the question is, can you get a moduli description? So obviously here, so we have a first approach, which would be, this is a hypersurface. Why not look at the GIT? Look at the GIT moduli of this hypersurface and then see how it compares to to the K modular. Okay, so let me, for the end of this talk, mention a few conjectures about those families which have both polystable and non-polystable members. So the first conjecture I'd like to talk about is the one on prime Fano threefolds of genus 12. So if I look at those, there's a description which is due to Mukai, who shows that prime Fano threefolds of genus 12 can be described as the Grassmannian of isotropic subspaces of the following form. So I take a 7-dimensional C vector space and a 3-dimensional C vector space. I consider a net of alternating forms on V, so a linear map from wedge 2V into N. And I consider the Grassmannian, the subspace of the Grassmannian of 3-dimensional subspaces of V, which satisfy which are isotropic with respect to the form eta. So the wedge 2 of V is in the kernel of eta. So so what do we know about these? So first I should say that this family is a 6-dimensional family. And this description is in some sense quite explicit, but still quite mysterious. So we know that there exists a unique element in this family which has automorphism group equals to PGL2. So how do you get this? Well, you take V to be a representation of SL2 in the above construction. We also know that there is a unique element in this family which has non-reductive automorphism. It has automorphism group GA semi-direct product mu4. We know that there exists a 1-dimensional family which have an effective GM action, and for all members except one element, which is the Mukai Umemura threefold with automorphism group PGL2. And we know that all other members of the family have finite automorphisms. So we know quite a lot about some of those special members. So here, Donaldson proved that there existed a Kähler-Einstein metric on the Mukai Umemura threefold. So Donaldson proved that X22 Mukai Umemura is K polystable. It's known that this one has a degeneration to the Mukai Umemura threefold. So it is K semi-stable, strictly K semi-stable. Because having a non-reductive automorphism group, it cannot be K polystable, but semi-stability is open, so it is K semi-stable. Then this 1-dimensional family has been studied quite a lot recently, and results of Cheltsov, Shramov a couple of years ago and Fujita a couple of months ago show that all of these are K polystable when U is not equal to 0 or 1. So the family, the effective GM action concerns the elements U not equal to 0 or 1 anyway. Okay, and then for all other members of the family which have finite automorphism groups, we know examples that are K polystable, and that's due to Cheltsov and Shramov, and not K polystable and strictly K semistable due to Tian. So quite a diverse picture. And here, so in a sense, we know what happens along a one-dimensional subfamily of this, but we have a six-dimensional moduli, and pretty much anything goes as to what's going on there. So Donaldson had a conjecture to describe non-K polystable elements. His conjecture was in a neighborhood of the point representing the Mukai-Uemura threefold. So here, a neighborhood of this point in moduli should be identified with a local analytic neighborhood of 0 in essentially the tangent space to the universal deformation space of the Mukai-Uemura threefold. So this is H1 of X, Tx. And this, because the Mukai-Uemura threefold is equipped with an SL2C action, is also equipped with an SL2C action. And so Donaldson's conjecture is that for any alpha in this local analytic neighborhood of 0, for any small alpha there, then the corresponding element of the family X alpha is K polystable if and only if alpha is GIT polystable with respect to the SL2C action. Now, Donaldson reformulated this conjecture and expects this to hold everywhere. So the equivalent formulation near the Mukai-Uemura point, which is expected to hold everywhere, is that X in the family is K polystable if it either has an effective GM action or if no element of the anti-canonical linear system has singularities worse than these here. So this is a really hard condition to check. And somehow the hope is that maybe, but that's very much like a very wild hope, which has little substantiation, is that you can relate it to some other GIT problem. And so Mukai had this alternative construction of these prime Fano threefolds of genus 12, starting from a plane quartic. So he shows that you have a birational map from the moduli of genus 3 curves to the moduli of prime Fano threefolds of genus 12, where essentially, if you start on the curve side, you have a plane quartic and you take the variety of polar sexagons of your quartic curves. So these are the 6 tuples of points in the Hilbert scheme of 6 points in the dual plane, such that F is the sum of 6 of the 4th powers of 6 linear forms. If you start on the side of the prime of Fano of genus 12, then the quartic is actually the Hilbert scheme of lines in X, and the plane on which it lies corresponds to the Hilbert scheme of conics on X. And so you have these special elements that correspond to special curves in this moduli space. And the question is, can you relate the K polystability of X to the GIT stability of your plane quartic? So of course, the reason why this is quite a difficult question is because we know that these two moduli spaces are birational. So you actually have an isomorphism on the space of smooth quartics, but you know, we don't, birational is not isomorphic. Maybe I'll stop here. I'll just say that there are some other conjectures for the other families, which in most cases, which are in the preprint, and in most cases try and relate, K polystability of the family to some GIT stability of a related object according to the Mori Mukai description. So I'll stop here. Thank you very much for your attention.